So we have our three equations. The top equation is specific to parallel plate capacitors, which is really all we're going to worry about. These bottom two equations work for any capacitors. It doesn't matter what type of capacitor we have. Now it turns out it's common to use more than one capacitor in your circuit in any given circuit, basically, for a couple of reasons. Number one, you can go to Radio Shack and you can buy capacitors, but they don't have absolutely every possible value of farads that you could possibly desire. Perhaps you need a 15 microfarad capacitor, but they only sell 10s and 20s. So you may need to use a combination of capacitors in order to get the capacitance you need. Another reason why you might use multiple capacitors is to minimize how much voltage, to minimize the delta V across each capacitor, so that you don't risk the chance of hitting the breakdown voltage of your capacitor. If you hit the breakdown voltage, basically the breakdown voltage is where the electric field is going to be big enough between the plates of the capacitor to actually physically force charges to jump from plate to plate, which then defeats the purpose of the capacitor. So breakdown voltage, not good to reach. So there's two ways to connect capacitors. One of them is in series. In series, we take capacitors and we connect them along one path. So we take a wire from the battery to one end of the capacitor. From the other end of the capacitor, we go to the next capacitor. From the other end of the second capacitor, we go to the third. And then we can go back to the battery. Now, to represent a battery in a circuit, we use a series of lines, long and short lines. The longer lines are the higher potential, the shorter lines are the lower potential. Whether you see a set of one or two doesn't really matter. A lot of times you'll see two. So a short and long line, that represents our battery. So our battery has some sort of total delta V, some total potential difference across it. Now if we think about what we talked about previously, we know charges are going to move until equilibrium's been reached. When equilibrium has been reached, the left end of the battery and everything it's physically connected to will end up being at the same potential. The right end of the battery and everything it's connected to will end up being at the same potential. But the left end is on the first capacitor, the right end is on the last capacitor. So delta V total has to be shared among these three capacitors. Each capacitor is going to have their own little delta V. So I'm going to call these C1, C2, and C3. They are not necessarily the same, so they can have different values. The potential difference across the whole thing, the delta V total, has to be shared amongst them. Each of them are going to have a piece of this total voltage. So the sum, delta V1 plus delta V2 plus delta V3, the sum has to add up to be the total voltage supplied to the circuit. This is conservation of energy. Whatever the battery puts in, the circuit elements have to take out. All of them will take out a portion. They will not necessarily take out an equal portion, but they will all take out a portion of that voltage. Okay? Charge. In order to reach equilibrium, there's a certain amount of charge that accumulated here on this left-hand plate, which is the same as the negative charge that accumulated on the right-hand side. So what's going to happen in the middle? If this plate's negatively charged, what's that going to do to the charges on the plate opposing it? It's going to push electrons away, leaving a positive Q. But the electrons, well, The only place they had to go was over to this plate, so this plate gets a negative Q, which in turn induces a positive Q on this plate, which in turn pushes a negative Q over to that plate. When you have capacitors in series, the total charge that the battery forces to move through the circuit is the same as the charge on each of the capacitors. In series, all the capacitors have to have the same charge. And that's because of induction, how the induction works. Another way to look at it, there's no place else for the charge to go. Whatever charge the battery pumps out, well, the only place it has to go is to the plate of that capacitor. There's no place else. Charge has to be conserved. You can't magically get rid of charge or magically gain charge. So whatever charge, by Q total, I mean the total charge that the battery pumps out, whatever total charge gets pumped out accumulates on the plates of that capacitor, which induces an opposite but equal magnitude charge on the opposite plate, and so forth across the line. So the total charge is the same as the individual charges that each capacitor has. So by Q1, I mean the charge on this guy, Q2, the charge on this one, Q3, the charge on that one. Okay, to figure out specifically how much potential and how much charge there is, we need to know on a whole what these three capacitors would be equivalent to. Okay, so we would know the individual capacitances, but they're going to be equivalent to one single capacitor with some equivalent capacitance. They're going to be acting as if they were one capacitor. To figure out how to do that, we're going to take this top equation. It turns out these equations here for capacitance and energy are valid for each individual capacitor. So C1 would be Q1 over delta V1. C2 will be Q2 over delta V2. C3 will be Q3 over delta V3. But it also works for the equivalent circuit. The equivalent capacitance would equal the total charge over the total battery voltage. So the the equation works for any individual capacitor or the system as a whole. And that's true for this one. I'm not going to write it out, but the energy for capacitor 1 will depend on capacitance 1 and delta V1, likewise for 2 and 3 in total. So, taking this top equation, in place of delta V, if I solve that middle equation for delta V, I get Q over C. So delta V total is going to equal Q total over C equivalent. Delta V1 is going to equal Q1 over C1. Delta V2 is going to equal Q2 over C2. Delta V3 will be Q3 over C3. This is helpful because we just said Q total is the same thing as Q1 and Q2 and Q3. They're all the same thing. So those all cancel. So we get this relationship that 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Using that equation, we could figure out the equivalent capacitance. By equivalent capacitance, we mean the overall capacitance that those capacitors are equal to in our circuit. If we know C equivalent and delta V total, which would be the battery voltage, it would then be easy to find Q total. Q total, using that middle equation again, would be C equivalent times delta V total. So we could easily find out how much charge totally moved in the circuit. Well, if we know total charge, then we know how much charge each of these capacitors ends up with. If we know charge and capacitance, using the middle equation, again, we can find delta V and find out how much voltage each of them comes up with. Okay? So basically, we're going to use the same equation over and over again. Break it down into one equivalent circuit to find the total charge, and then work backwards. So let's do an example. So let's say we have three capacitors. One's a 5 microfarad capacitor, one's a 10 microfarad capacitor, and one's a 20 microfarad capacitor. They're connected in series. In series, there's always one right after the other. If you were to take a little field trip and trace your way around the circuit, you have to pass through all three. Our battery is a 10-volt battery. What I would like to find is delta V, the potential difference across each of these individual capacitors. Well, let's just go for that right now. So delta V across this capacitor, delta V across this one, and delta V across this one. We know that the sum of these delta V's has to equal 10 volts. So whatever these three are, they're going to add up to be 10, but they're not going to be equal. They're not all going to be 3.33. Why not?
Capacitors aren't the same size.
Capacitors are not the same size. In series, we know they have to have the same charge, but if the capacitors are not the same size, then delta V can't be the same for all of them. So what we want to do is we first want to take a step down here and say, well, these three capacitors are equivalent to having one single capacitor connected to our 10-volt battery. So they're equivalent to what is what we're looking for. So to find equivalent capacitance, we have this 1/over relationship. And by the way, you just add them all 1/over regardless of how many you have. In this case, we have three of them. So we end up with 1/5 plus 1/10 plus 1/20. Let's get common denominators. 4, 5, 6, 7/20. And most common mistake is forgetting that this is 1/, it's the equivalent. So the equivalent capacitance in this case will be 27 microfarads, which I'm not a huge fan of using fractions. So I'm going to give us a decimal place.
I wish all my teachers were like that.
I'm sorry, what?
I wish all my teachers were like that.
Now this is a rounded number. 20 divided by 7 isn't a nice, easy number. So this equivalent capacitance, having those three capacitors in series is equivalent to having one capacitor that has a value of 2.86 microfarads. You okay with that? That part's all right? If we know the battery voltage, that's the delta V total, and we know the equivalent capacitance, we can use our middle equation using the total information, and we can solve for Q total. Q total will be the equivalent capacitance times delta V total. So it will be the 2.86 microfarads times our 10 volts. So 28.6 microcoulombs. The farad times a volt is a coulomb, because the farad is the same thing as a coulomb over a volt. So the total charge that this circuit forces to move around is 28.6 microcoulombs. So this battery is pushing out 28.6 microcoulombs. So 28.6 microcoulombs accumulates on that particular capacitor. By induction, it also accumulates on this capacitor, and likewise on this capacitor. All three capacitors end up with the same charge. So the Q, they all end up with the same Q value. Well, we now know C1 and Q1, we know C2 and Q2, we know C3 and Q3. Using the exact same equation over again, but now for the individual capacitors, if I know Q1 and C1, then delta V is going to be simply Q over C. So the voltage across our first capacitor is going to be 28.6 microcoulombs divided by 5 microfarads. 5.72 volts for that first guy. 2.86 volts for that guy. .43 volts for this one. Now, one thing to keep in mind, if I add those three together, they should equal 10. But if I actually add those three together, I get 10.01. Where's the discrepancy?
C.
We rounded this. 20 divided by 7 is not exactly 2.86. So we're using a rounded number here, which in turn means this is a rounded number, which in turn means those are rounded numbers.
So do you want us to keep a lot of decimal points or choose fractions in the test?
You can use decimal points, are fine. You don't need to use a ton. I'm not worried if you get 10.01 instead of 10. Questions on that so far? So we had to break it down, simplify it, figure out what they would be equivalent to in order to find the total charge. We know the total charge is the same on each of them, so we could in turn find the delta V. So basically we use this equation over and over again. It would be very easy to find the energy that each of them stores. The energy that capacitor 1 stores, we would need capacitor 1 and delta V1, which we have. We can find out how much energy it stores, and likewise for each of them.